The following theorem ties together linear dependence and the Wronskian. So if y1, y2, up to yn are n solutions to the differential equation, the nth derivative of y plus p1 times the n minus first derivative of y plus dot 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 plus pn times y equals 0 on the interval a comma b with p1, p2 through pn continuous functions on the open interval a comma b, then the following statements are equivalent. 1. y1, y2 through yn are linearly dependent on the open interval a comma b. 2. The Wronskian w of y1 through yn at x naught is 0 at some point x naught in the open interval a comma b. 3. The Wronskian w of y1 through yn of x is identically 0 on the open interval a comma b. The contrapositives of these statements are also equivalent. 4. y1 through yn are linearly independent on the open interval a comma b is equivalent to 5. The Wronskian w of y1 through yn at x naught is non-zero at some point x naught in the open interval from a to b. And 6. The Wronskian w of y1 through yn of x is never 0 on the open interval a comma b. Whenever 4, 5, or 6 conditions 4, 5, or 6 are met, the set y1, y2 up to yn is called a fundamental solution set for the differential equation, the homogeneous differential equation on the interval a comma b. So in this example, we will show that 1 comma x squared is a fundamental solution set to the differential equation y triple prime equals 0. So in order to show that a set of functions is a fundamental solution set, we need to show two things. So the first thing we need to show is that each of these functions is a solution to the differential equation. 1x and x squared are solutions to y triple prime equals 0. So in order to show that, we just need to take the third derivative of each of these functions. So if we take the third derivative of 1, that equals 0. And if we then take the third derivative of x, that is going to be 0 as well. And then finally, the third derivative of x squared is 0 as well, because x squared goes to 2x, goes to 2, goes to 0. So that checks out. Now, according to the previous theorem, we need to show that either 4, 5, or 6, conditions 4, 5, or 6, one of them needs to be met. So we will show that the Wronskian is never equal to 0. So, but you could also just show that it's not 0 at some point. So we're going to show that the Wronskian of 1x and x squared is never 0. So the Wronskian of 1x and x squared is given by a 3 by 3 determinant, and we write down 1x and x squared. Then the second row of our determinant is the derivatives of these functions. So derivative of 1 equals 0, derivative of x equals 1, derivative of x squared is 2x. And then the final row in our 3 by 3 determinant will be 0, the derivative of 0, 0, derivative of 1, and then 2, derivative of 2x. Now, in order to compute this 3 by 3 determinant, I'm going to apply the trick that we discussed earlier. So I'm going to copy down the first column, and then I'm going to copy down the second column. And now I'm going to look at the diagonal products. So I have 1 times 1 times 2. So that gives me 2 plus, and then x times 2x times 0. That gives me 0 plus, and then the third diagonal is x squared times 0 times 0. So that gives me 0. And now I'm going to look at these diagonals here. So I need to subtract that. 0 times 1 times x squared, that gives me 0. 0 times 2x times 1, that gives me 0. And then 2 times 0 times x gives me 0 as well. So the final answer for this Wronskian is 2. And our conclusion is that the condition 6 is met. So condition VI, or condition 6 from theorem 3, is met. And so therefore we can conclude that the set 1x comma x squared is a fundamental solution set. Of this homogeneous differential equation. So another way of saying that is that these three functions will be the building blocks to any solution to this differential equation. So as soon as we're going to put in some initial conditions, we know that whatever our initial conditions are, it will always, the solution will always have the form C1 times 1 plus C2 times x plus C3 times x squared. So let me write that down here as a conclusion. So the conclusion, or another way of thinking of this, is that any solution to y triple prime equals 0 has the form C1 plus C2x plus C3x squared. So now we're ready to move on to the non-homogeneous case. So If we combine the linearity or superposition properties of the linear differential operator L with the representation theorem for solutions of the homogeneous equation in theorem 3, we obtain the following representation theorem for non-homogeneous equations. So if yp is a particular solution to the non-homogeneous equation given by the nth derivative of y plus p1 times the n minus first derivative of y plus plus pn times y equals g of x on the open interval from a to b with p1 through pn continuous functions on the open interval a comma b, and if y1 through yn is a fundamental solution set for the corresponding homogeneous equation given by the nth derivative of y plus p1 times the n minus first derivative of y plus plus pn times y equals 0, then every solution of the non-homogeneous differential equation on the open interval a comma b can be expressed in the form y of x equals yp of x plus c1 times y1 of x plus plus cn times yn of x. We will show a proof based on theorem 3 of this theorem in the next video.